This video is going to tell you a little bit about capacitors, capacitance, and the energy stored in them. To begin with, capacitor is just two parallel plates of metal for all intensive purposes for what we're doing. In this little circuit that I have in the upper left-hand corner, I've got two little parallel plates connected by a wire to a resistor, which really is a light bulb. That's what the LB is for. Now, capacitance is defined as the ratio of charge to the potential difference. That's delta V, whereas the potential is measured in units called volts. So C is the capacitance, measured in farads, named after Michael Faraday, who we're going to talk about later. Q is the total charge on the capacitor. That's the charge on either plate. It's measured in coulombs. So if I have these plates up on the screen, one plate might have, say, 10 coulombs. The other plate would have negative 10 coulombs. And Q, the value you'd use would just be 10 coulombs. So it's just the charge on one of the plates. And it's, in this case, absolute value of the charge. So don't worry about the negative. And finally, delta V, that's the potential difference, which is the voltage across these two plates, and it's measured in volts. Now, a farad is defined as a coulomb of charge times divided by the potential difference of 1 volt across the plates. If I was to make up a farad using electrons, then it would take more electrons than are in Avogadro's number. That's 6 1/4 million electrons. So it's a lot of electrons. Or 6 1/4 million electrons. It's a lot of electrons, just an amazing amount. Now, our formula for capacitance, I'm going to rearrange it in terms of Q. So C is equal to delta V, which is equal to Q. What this is showing me is that the potential difference on the plates is directly proportional to the amount of charge on the plates. And that's going to become important. Because see, the main function of a capacitor is to store energy. And I know from previous stuff that we had in the past, when we had two plates, and we had charges going across these two plates, that the work done to move the charges across the plates was equal to QV, Q delta V. And that was the energy that's stored in the plates. But now that I'm talking about these capacitors, the energy stored in the plates, it's not quite that simple. The energy is not just the work, but the energy stored in the plates is actually 1/2 Q delta V. That's 1/2 the charge times the potential difference. So the real question here is, how come these two things aren't the same? Why is the energy stored not equal to QV? So here's why. And this is good because it'll help you understand what a capacitor does, kind of how it works in a circuit. So our formula for finding out the charge on the plates of the capacitor is equal to C times delta V. That's the capacitance times the potential difference. They're directly proportional. So whatever happens to Q also happens to the voltage, or the potential difference on the plates. I'm going to connect a resistor or light bulb in between my two plates, and when I do that, this gives the charges a path to follow. So they'll feel electric field through the wires that'll move them across the light bulb. And they're attracted, so one will move from one side to the other. Now I'm using positive charges instead of negative charges because I'm always concerned with energy flowing from high to low, which in this case would be from positive to negative. So I'm not talking about the fact that electrons actually move. We're talking about how the energy flows and if positive charges are moving. Alright, so beyond all that, I've got these charges moving to the other plate. When the positive and negative combine, they eliminate each other. So now I have less charge. Instead of having 4, I've got 3. So less charge means less potential difference, less voltage. And this process happens again. And the charges combine, gives me 0. So now instead of having 3 charges on each side, I have 2 charges. So again, Q gets smaller. And then it happens again. The charges combine, eliminating each other, giving me 1 charge on each side. So now I've got less charge, I've got Q, so delta V is smaller still. So as this is going on, it has lower and lower potential difference. So it's able to give off lower and lower and lower amounts of energy as it travels through the resistor. What we'd see is the light bulb getting more and more dim every time a charge passes across the light bulb because the potential difference between the two sides is smaller and smaller and smaller. Finally, the last charge moves across, which means I've got nothing. So now delta V is equal to 0 because I don't have any difference in charges. No plus and minus on opposite plates. So that's it. Basically, the capacitor is done. All the energy is out of it. So if I look at this, I start off with 4 charges in the beginning. That was my delta V. Now at the end of this whole process of emptying out the capacitor, my delta V is equal to 0 charges. So if I look at this over time, the average of 4 and 0 is 2. In other words, it's 1/2 the maximum potential difference. So if I go back to my equation, the energy stored is equal to 1/2 Q times the maximum potential difference. That's my delta V. So E is equal to 1/2 Q delta V. And just as an aside, there is kind of another equation of convenience. And what you can do is you take your equation for capacitance, solve it for Q, like it's shown on the screen, and then take C delta V and plug it in for Q in the energy stored equation. And that gives you one more equation, which is kind of convenient to know. The energy stored is equal to 1/2 the potential difference squared.